All right, so now we are working on combining the transformations based on the parent graph of f of x equals x squared. So our essential question, how can you obtain the graph of g of x equals a times x minus h squared plus k? So how can you obtain the graph of a quadratic function in vertex form? By comparing it to the parent graph. Well, remember, if we look at this, we have a, which is what? Right, that tells us whether we're going to reflect across the x-axis, and it tells us whether we're shrinking or stretching or not. And we also have h and k, which are our vertex, which are the coordinates of our vertex. And now we are combining those by the powers of, all right, that's too cheesy for me. All right, so we started with a sequence. So we're understanding how to graph in vertex form when we have both a and we're using h and k. So this is the sequence they say to start with. Step 1, start with the parent function, the graph of y equals x squared. So they've graphed that for us. Step 2, well, because a is 2, we're going to stretch it vertically by a factor of 2 to obtain the new graph. So here it is stretched. And then step 3, we're going to translate the graph, right 3 units and up 1 unit to obtain our new graph. So we just went right 3 and up 1, and there's our new graph. Yeehaw! That looks like a lot of work to do on paper, though. That would be insane to do that all the time. So we're going to learn how to do that without having to do all of that on paper. So here I just drew these for us again, and here's our final graph. Here's our big function, and here's the parent graph to compare. So, well, the vertex of our parent graph, there that is what? Well, 0, 0, right? And while the vertex of the graph of g of x equals 2 times x minus 3 squared plus 1 is, if we look at that, that's actually, we don't even need to look at this, do we? We've got it right here. We have our h, which is the opposite of negative 3, and our k, which is 1. So that vertex is 3, 1. And sure enough, that matches. Well, if we start at the vertex, now this part gets a little weird. And you just trust me, I know where they're going. They get you there in a weird way, but it's going to make sense. So if we started at the vertex here of this graph, there's our vertex. And we move 1 unit to the right or the left. Let's move 1 unit to the right. Then what do we have to do to get back to our graph? We have to move 1 unit up. So we're kind of looking at slope. We had to go over 1 and up 1 to get back to our graph. So we had to move 1 unit up. Okay, now if we start at the vertex of g of x and move 1 unit to the right or the left, so let's start there at that vertex, and we move 1 unit to the right or the left, it doesn't matter, let's move to the right. How far do we have to move vertically to get back to our graph? We have to move 2 units up now. So we had to move 2 units up. So the reason that we're looking at this is because we would always, for our parent function, be moving over 1, up 1. But depending on what a is, that's just going to move us up that much steeper. Or if a is less than 1 but greater than 0, it's going to move us up fractionally less, right? If it's 1/2, it's just going to move us up to 1/2 there. So we can use that 1 to the right and 1 to the left to really easily see what I could kind of call our slope of our parabola. And now this is kind of a weird way to say it. So based on this, how would we graph g of x directly without having to use these transformed graphs? Well, what we could do is we could just use the vertex, hk, so we'd start with that, and then we would use 1 point to the right or the left, and we would use k plus a to draw those points. So we'd go from the vertex, we'd move 1 right, and we would just add a. We would move 1 left, and we would just add a. And then we could estimate the rest of our graph. And so we're using k plus a. So k was our y coordinate of our vertex, A is moving up further. Or, of course, if A was negative, we'd be moving down, right? To draw the points. Another way to say it is we'd have these 2 points, h minus 1, so to the left of h, comma, k plus a. So this would be our x, this would be our y. And h plus 1, so 1 to the right of h, comma, k plus a. So this would be our x and our y of our second point. And that would give us a starting point for our parabola, and we wouldn't need to make a table anymore. So let's practice that. Here we have g of x equals negative 3 times x plus 1 squared minus 2. What's our vertex? That's right, there's h, which is negative 1, the opposite of 1, minus 2, and k is minus 2, negative 2. Okay, negative 1, negative 2. Let's go ahead and draw our graph in the middle because we have got room. If we have our vertex here, that's so close to the center, we can just center label our scale, and plot our vertex. All right. Okay, so now it wants us to identify and plot points based on the fact that our parent function, if we plugged in 1 or negative 1, we would get an output of 1. That's always true for our parent function, right? Because that's simply f of x equals x squared. So basing that, using that, what could we do for g of x? Well, if we move 1 unit right or left from the vertex, how much would we have to move vertically to get back to the graph? Well, we would have to move vertically down 3 units down, because that's our a, is negative 3. So we'd have to go 3 units down. That's going to give us negative 2 comma negative 5, 0 comma negative 5. So if we think about this another way, if we start here and we move 1 unit to the right, well, a is negative 3, so we'd go down 1, 2, 3, and we'd have a point of 0, negative 5. And if we move to the left 1, and we plug that in, we would, because a is negative 3, we'd go down 1, 2, 3, and we'd have that as our output. And so we can plot those points, and we can draw our parabola. Now, it's not perfect because we're not plotting all the rest, even though the pattern holds true, but this is good enough to get us started. Okay, so now it's just asking us to list the transformations we would do in the order that we would do them. Well, the proper order is the first thing we would do is we would look at A, which is going to be a vertical stretch by a factor of 3. Our A is also negative, which means we would reflect across the x-axis. And now we could look at our H and our K, and we could say, all right, our H is negative 1 and our K is negative 2, so that means that we would translate 1 unit left and 2 units down. Okay, before graphing this, would we have expected the graph to open up or down? Why? It's negative, A is negative, so of course it's going to open down because A is a negative number, so the function is reflected across the x-axis. And then what would happen if we changed our A from negative 3 to negative 4? Which of the points that we identified in the first part when we graphed this originally would change? And what coordinates would they now have? Well, our vertex would stay the same. H and K would still be the same. All that would change is our A, and we're going from negative 3 to negative 4. So instead of going over 1 and down 3, now we'd be going over 1 and down 4. So the new coordinates that we would have is we would have the points in part B would change to, well, let's see. If we're moving left 1, so it's negative 2, and now instead of moving down 4, we're moving down 3, we're moving down 4, what would we have? We'd still have a point. Our x would be negative 2, and our y now would be negative 6, because we moved down 4. And then on the other side, we would have an x of 0, and again a y of negative 6. This is just going to take practice for you to get, okay? All right. Okay, so let's go to a word problem, because those are easier, right? All right. I'll let you read this. So go ahead and pause and come back when you're done reading it. Okay, so to find an equation for f of x, we're going to start with a vertex of the parabola. So that's our 0, 30. 0, 30. And if we substitute the values of h and k in, we can put those in to get a general equation. So f of x equals a times t minus 0 squared plus our y of 30. Good. So that's our basic function so far. But what do we still need? We still need a. So we'll solve for that. From the graph, we can see that f of 1 equals 14. So now we have another x and y that we can substitute in. We're going to substitute 1 for t and 14 for f of t to determine the value of a for this function. So we're solving for a. So we're plugging in 14 for our f of t, or our y, equals a times 1, that's what we were given from our point, 1 for t, it gave us that, minus, as we figured out before, this is minus 0, plus, as we figured out before, plus 30. And now we can solve for a, and it didn't really give us room, so I'm going to do it over here. So we've got 14 equals a times 1 squared plus 30, because 1 minus 0 is 1. We can just do that math. 14 equals a plus 30. Subtract 30 from both sides. Negative 16 equals a. All right, so a is negative 16. So write the equation for the function. I'm going to write the function as we had it before down here, just for reference. You have it on your paper. F of t equals a times t minus h squared plus k. So f of t is going to equal, what's our a? That's right, negative 16. T minus h squared, well, h is 0, so that's just going to be t squared plus, what's k? Plus 30. There's our equation. Now, how can we figure out whether or not we're right? Well, let's look at our x-intercept. When does it hit the ground? Oh, it looks like it's about 1.4. We can't quite be sure, but it looks at about 1.4 seconds. And then if we use that value, and we plug that in, then we could see whether or not we're on the right track. So let's put that in. So f of 1.4 equals negative 16 times 1.4 squared plus 30. And then through the magic of a video, I can tell you that that equals negative 1.36. So in 1.4 seconds, it's negative 1.36 feet from the ground. So that's pretty darn close to 0, isn't it? So because that's so close to 0, we're going to say that this is, remember, we were estimating that 1.4, weren't we? We weren't sure about that. So this is as close as I think we can get from just estimating it from a graph. So since f of 1.4 is close to 0, which is what we were looking for, that's our expected value from the graph, we can say that the equation is reasonable. Is it perfect? Not necessarily. But gosh darn, telling from this, we can sure say that we are on the right path. Okay, so for your homework, one of the things that they ask you to do is graph each quadratic function. In the past, you made a table. I'm going to ask you to stop making tables. So I'm going to do the first one very quickly for you and then ask you to try it on your own afterwards. So I looked at my h and my k to get my vertex, which is 2, 3. I looked at my a, which gives me 2. I figured out where my origin should be. I graphed my axes. I plot my vertex, which is 2, 3. And then I said, all right, if a is 2, I'm going over 1 and up. Over 1 and up 2, going back 1 and up 2, plot those points, drew my parabola, and I'm done. Okay, try that. Do your best on your homework. See you guys in class.